This meeting is being recorded.
So, good afternoon, everyone, and a warm welcome to all the participants. It is with great pleasure that we extend a warm welcome to Dr. Tabish Alam, a senior scientist at the Central Building Research Institute, Roorkee, as an expert resource person of this online FDP program on smart building design at NIT Patna. We are honored to have you conduct a hand-on session on CFD analysis of thermal systems using ANSYS Fluent, and your expertise in computational fluid dynamics and thermal system modeling brings an immense value to the participants, particularly to understand the advanced simulation techniques and their application in the energy efficient buildings designs. So once again, we warmly welcome you, sir. And now I call Subham Meena, sir, to briefly introduce the expert to the participants. Meena, sir, please introduce the.
Thank you so much, Ravi, sir. Good afternoon.
हाँ देख रहा हूँ वॉल्यूम आ रहा है म्यूट कर रहा हूँ
Hello, sir. I hope now everyone can hear my audio. Thank you so much, Ravi, sir. Good afternoon, everyone.
एक नहीं आ
It
रहा है
gives
आपका
me a great pleasure to introduce our esteemed speaker for this session, Dr. Tabish Alam, Senior Scientist at Alam is a leading expert in heat transfer and solar thermal systems, computational fluid dynamics, and regulatory. He holds both Ph.D. and in thermal engineering. His research career includes postdoctoral work at IIT Roorkee and Stanford University in South Africa. Dr. Alam on sustainable energy and thermal engineering has found and application was mainly involved among the top percent scientists globally by Stanford University in 2024. He is also a recipient of several prestigious honors, in climate change technology award and Tabish Award. Dr. Alam is actively shaping national standards as a member of the BIS committee on thermal insulation material and contributes to the global research community as associate journal in various journals like thermal science and energy system, energy efficiency in building and urban environment, journal of engineering. And he is also a member of editorial board for scientific report by Nature publishing group. With a vast body of work published in high-tech journals, Dr. Alam and at the forefront of energy efficiency and thermal optimizing building systems. We are honored to have him here today to speak on CFD analysis for thermal system using ANSYS Fluent. Please join me and we warmly welcome you, Dr. Tabish.
Thank you, Subham, sir, for briefly introducing the session expert to the participants. And now I would like to the session expert, Dr. Tabish Alam, to please start your sessions.
Hello, am I audible?
Yes, sir, audible, sir.
Okay. So thank you, Shubham and Ravi for introducing me in the audience. So basically, in the today's session, we will uh, uh, we will do the some tutorial in the ANSYS Fluent how we can do the simulation of the thermal system, how we can utilize this tools to simulate the different thermal system, not even the solar thermal system. We can analyze the any thermal system, not basically we have my student or my trainee student will with also with me. So he will show he will share their screen to show how to do the simulation in the Fluent. So first we have a short presentation on our previous paper where we will show how we have conducted the simulation and how we get the results. So and later on we will do the simulation different simulation techniques in the ANSYS Fluent. So let me share my screen. My screen is visible.
Yes, sir, it's very well visible.
Basically, is one of the paper from my group that has been presented in the FMFP that has been held last year into the legal. So basically, in this system, we have in this paper we have carried out the thermal analysis of the micro channel that have the different diverge rift geometry in that. So we have carried out these simulation using the Fluent. So basically, in this short PPT, we have different content like introductions, computational model, channel orientation, mesh sensitivity, governing equation, boundary condition, results, and the conclusion. So basically, in the microchannel heat sink, that is a very small thermal system that can be used for the cooling of the electronic component. It is dimension in the micrometer, so it is known as the microchannel. In microchannel, we have a cooling fluid is there which can extract the heat from the electronic component. So microchannel heat sink is the advanced cooling solution that dissipate the heat, that extract the heat, which is 50 times more higher compared to the conventional. So the efficient cooling device that this cooling device can be used in the electronics, micro heat exchanger, micro refrigerator, and the fusion devices. So demand of such there is a lot of system is there. We have a high density heat flux is there, so we have to remove this heat high heat density because it do not remove the heat from the system, so it can be damaged. So there is a challenge to extract these heat. So we have the force convection over there. We have the air is flowing over the fin like structure. It can remove the heat, but we have the micro channel heat sink where we can use the liquid that is liquid based cooling. So basically the liquid has a high heat carrying capacity, so it can heat the maximum amount of the heat. So basically, these are the few example like in the electronics microchannel are as the integrated microchannel network and the liquid cool thermal spreader coupled to air cooled air sink for cooling semiconductor chip. So it can be used into the air conditioning system, heat pipe technology, and solar energy system. Solar energy system basically in the PV panel, the solar photovoltaic thermal collector, it has a wide application, and we are working in that direction. So we are working. We can integrate the micro channel into the PV panel, so we can extract the heat. So this heat not only utilized to heat the heating purpose, or we can reduce the temperature of the PV cell. So basically, these are the few micro channel where we have conducted the heat thermal analysis. So these are the models we have prepared in the ANSYS Fluent. So in that you can see this is the plan view of the micro channel, and this the light color is shows the fluids. So there is a diverge rib is there. It is a circular rib. It is a triangular rib. It it has a different shape, and this has the conical shape. So these ribs we have this there is a S circle, S triangle, S octagon, S hexagon kind of the ribs is there in the domains. So basically the and we have taken the pitch of 0.4 mm. So basically this is the optimized pitch we can use in the analysis of the microchannel heat sink. So this is the model. Basically this is the we have taken the one uh, channel. So in that channel we have fluid inlet at the one end and fluid outlet at the other end. So there is a total 25 if there, and the total length is the 10 mm. 10 mm is the total length is there. So it has a dimension in the dimension is very small. So we have taken four type of the rib: S circular, S triangle, S octagon, and S hexagon rib in that. So we also there is a few step is there in the CFD. We first we have to make the geometry using the design modular. Then we have to do the meshing. So meshing is the only the process which can convert the whole domain into the millions of the small volume is there. So you can see there is a described this the volume has been described converted into the small volume. So there is a millions of the volume which make the single volume the fluid, that is the fluid domain, and that is the material of the micro channel. So these two domain has been categorized. One is the fluid domain, one is the solid domain. So basically, so in that we have conducted the mesh sensitivity. So basically the mesh sensitivity is the nothing but it is the analyze the effect of the number of node with the result, how number of node we can increase and how the result is deviating. We have carried out the these simulation for the different nodes. We have taken 14 lakh 82,000. We have taken the node 20 lakh 23,000. We have taken the 25,000 nodes. So the we have compared the temperature, and you can see that there is a minimum error is has been found. It is around 0.05%. So we can say the 4 lakh 14 lakh 80,000 is the optimum number of the node we can utilize in the simulation. So basically in the whole this is basically the numerical tech methods in which we have to we have to analyze the equation whatever the what different energy different equation like momentum equation, energy equation that has been utilized to describe the whole domain and the physics of the simulations. So these are the equations. That is the continuity equation. It is the momentum equation in the x direction. This is the momentum equation in the direction. This is the momentum equation in the z direction. This is the energy equations. This is the energy equation for the fluid, and this is the energy equation for the materials. So basically, the next step is to uh, First step is to make the model. Second step is to make the mesh of the developed model. Then we have to apply the boundary condition and the initial condition. So there is a these are the template we can seen here. We can seen here is the template of the inlet condition. So we have the inlet boundary condition where we have use the velocity inlet outlet condition, where we have the pressure outlet condition, and we can apply the heat flux on the base, and we can take the side wall of the microchannel as the symmetry to minimize the computational effort. So these are the basic the inlet basic boundary condition of the system. So the we have used the laminar model in this simulation, and we have taken the Reynolds number from 100 to 900. Sorry. 100 to 900. So in this system, two type of the heat transfer is there. One is the conduction, one is the convection. So in the modeling of the this CFD, so we have a lot of assumption is there, like we have the uniform heat flux applied over the base of the channel, and we have the uniform velocity inlet. We have the constant property of the fluid as well as the micro channel, and we are not counting the radiation heat transfer that has been negligible. So basically we can assume that the no slip condition is applied on the wall. So these are the few conditions. So these are the result we are get for the S channel. We this is the contour of the temperature of the base of the passage. So this is the for S type fin. This is for the S triangle. This is for the S octagon. This is for the hexagon. So this is the temperature reaches up to 319 degrees. So its diagram shows the location of the this contours. So basically these are the contour of the temperature of the base of the passage, and this shows the contour of the temperature on the mid plane of the passage. So these are the result. We can compare these result how the temperature is deviating from inlet to outlet in the due to the different ribs. So we can compare the temperature, we can compare the velocity, we can compare whatever the parameter we have, we can compare using these contours. So this is the contour of the temperature of the mid plane. So you can see the higher temperature at the outlet has been obtained at the S type ribs. So and the minimum temperature is achieved in the S type fins at the outlet section. So these are the few result we have extracted from these ribs. So these are the velocity contour due to the rib. This is the basically this shows the uh, plan view of the fluid domain, where we can see the this rib portion. This is the S type rib, this is the T type rib. So there is a different type of the rib we have taken. So this shows the velocity contour over the length of the micro channel. So these are the velocity contour, and these are the pressure contour. So you can see there is a we can analyze the pressure, we can analyze the velocity, we can analyze the temperature, we can analyze the pressure. So these techniques, these contours are very useful to comparing the CFD result. So these are the few results. So these are the result in the quantitative values. So we have been calculated the result in the form of the Nusselt number and with respect to the Reynolds number, and we have extract the base temperature with respect to the Reynolds number at different rib shape. These are the pumping power required to flow through this channel. So the smooth channel we have the S rib, S triangle, S octagon, hexagon. So this result has been compared with there is a no channel is there for the smooth channel. So you can find that due to these reef the pumping power requirement is too high. Simultaneously, it's also in the previous slide we have seen the Nusselt number of these reef is too high in comparison to the smooth channel. So this is the overall thermohydraulic performance that has been considered based on the enhancement in the Nusselt number and enhancement in the friction factor. You can see the thermohydraulic performance continuously increases with the Reynolds number of the different ribs. So basically these thermohydraulic performance when the THHP value is more than 1, so it is the beneficial for utilizing these techniques. So you can see at a low Reynolds number the THHP is 1. When the Reynolds number is too high, that we are getting the higher THHP values. So these are the results which help to design the different ribs which would have the higher thermohydraulic performance in terms of Nusselt number and the friction factor, that is the pumping power. So these are the conclusions. So basically this is the first paper. Then we will take you to the one example of simulating this type of the micro channel heat sink. So let me stop here. My student will share the screen of their computer, then we will start how to do the simulation in the CFD. You can share. Yes. It is visible to all?
Yes, sir, it is visible.
Okay. So basically these are the interface ANSYS workbench. So there is a number of on the left hand side you can see there is a number of the different module is there. Coupled field harmonic, coupled field model. So there is a number different type of the simulation can be done. So we are going to do the fluid flow simulation. So that can be done into the Fluent. So you can see that this uh, tab. So where though Fluent has been initiated, so there is a few steps is there in the Fluent flow. The first step is the geometry. So first we have to generate the geometry, then we have to do the matching, then we have to do the setup, then solution, then the result. So in the geometry, you can open. You can change from the default. इसमें कर सकते हो?
It will open, sir. I can do in the discovery also, and I
Okay.
will cut it and then change
Okay.
it to
Okay.
the design module.
Okay. This software is very bulky, so it's take time. So these the design modeler of the ANSYS Fluent. There is a different kind of the design modeler is there. This is the one of the design model generally I use. Uh, yes, so you can see here we can change the dimension in meter, centimeter, millimeter, micrometer, feet, inch. So on the basis whatever the requirement we can generate, we can use the units. So we will make a one channel. So there is a few steps to generate the 2D geometry or the 3D geometry. So basically, this is the XY plane where we can generate the any sketch. So we will generate the sketch of the one micro channel. So there is a line by line we are sketching the sketch of the micro channel. So we can give the dimensions. You can give the dimension like this. So 0.35 mm is the width, half width of the micro channel, and height is 0.2 mm. So this is the one of the sketch of the micro channel. So we can set the dimension from this. So now we from the sketch we generate the 3D model of the micro channel. So basically this is the material we have. This is the material. Now we this is the solid domain of the micro channel. So we have to create the fluid domain within this micro channel. So there is some method to create the fluid domain also. So we have infill, fill pattern, fill option. So we can select the wall, one wall, two wall, and the third wall, and we can create. So this is the second domain is there. So you can see there is a two part is showing it there. This there is a one domain and this is the second domain. We also can rename of this. This is the fluid domain and so upper one is the solid domain. You can see here. So we created the two domain basically. One is the fluid domain, one is the solid domain. So if you want to change the further geometry, so we can hide that one domain. We can uh, we can see how the fluid domain has been hide. So we can uh, modify the geometry of the solid domain. So in this way we can generate any kind of the geometry of the fluid domain as well as the uh, solid domain. This is the one step. This is the one step is there. Now we have the second step. That is the meshing. So we have completed the geometry. It means we will go to the next step. That is the meshing. In the meshing, we discretize the whole geometry into the millions of the small volumes of the fluid domain as well as the solid domains. So in this we can generate the meshing. So there is a number of option is there. The result mainly dependent on the type of the meshing. So there is a different kind of the meshing available to do. So we can do the sizing, we can generate the unstructured meshing, we can do the structured meshing. So basically, generally we prefer the structured meshing. So step by step we are doing the hexadominant. We can generate. ये देना भाई. Try करना, yes. This is the meshing has been done, so you can see that volume it is discretized into the different volume. So this is the second step, but we can improve the meshing. We have defined the element size, whatever the size we defined, so it's refine the meshing of the each domain, each volume. Okay. So matching is going on. So it will take time. When we increase the meshing, decrease the meshing size, or we go for the uh, fine mesh, so it will take time. So you can see there is a millions of the small domain is there. Now, generally, we prefer the fine meshing as the joints. So, there is a domain which is adjacent to the solid domain. So, we need to do the fine meshing at that surfaces only. So, in that, we can implement the inflations. So, in the inflation we have to select the phase where we have to make the fine mesh, and we have to give the minimum layer and the growth of the growth rate, that is the 1.2. Generally we prefer 1.2 growth rate, and we can increase decrease the maximum layers. So So you can see here there is a mesh size is very fine at the edges. You can see there is a very fine mesh is there at the edges. We are going to further refine the mesh. When we increase the number of mesh, it will take time, and but the result is very good. So meshing is going on. Now it has been done. So you can see the further we have refined the mesh. This is the solid domain, and you can see the domain of the fluid is also discretized into the millions of the nodes. Now we this is the second step. This is the very important step for doing the meshing, because most of the result is dependent on this method only. We can check how many nodes we have. We have generated the nodes for 4,71,000, and the element is 18 lakh, around 18 lakh. So we can go to the next. Before going to the next step, we have to define the different surfaces for application, for applying the boundary condition. So where we have the fluid inlet, where we have the fluid outlet, we have to locate. So in this process, we will show how to give the naming of the different surface. So in the inlet, the red one is, sorry, red one shows the inlet surfaces where we can inlet the fluid into the fluid domain. Now the outer faces. So these naming would help us to identify the different surfaces. And this is the base where we apply the heat surface. And all the default, when we do not choose, we do not select the faces, so it will automatically give the name to particular face which do not be named by us. So now we can go to the next step. So different naming has been done. Now we can update the mesh step. So there the tick would be there. So basically we have the 14 lakhs node. So it will take time.
अरे इसलिए इसलिए जला दिया कि तुम्हारा आंख नहीं खुल रहा था।
So the setup is ready to apply the different boundary conditions. So here we can change the how we can need the result, double precision, single precision, and we use the different processors simultaneously. So in that we are using only one solver, one processor. So for this particular tools, there is a different workstation is there. So basically, very high computational power is required to solve these to use these tools. So till now we have generated the domain and we have done the mesh. Now the next step to give the property of the fluid domain in the material, and we have to give the inlet boundary condition, initial boundary conditions. You can decrease the mesh. Because due to the high node number of nodes, the it's taking the time, so we are decreasing the number of nodes. So we are going to decrease the number of nodes. So
वो जो डायलॉग मैनेजर रहता है वो बंद कर दिया था, तो रिसेप्शन में वापस आता वो आएंगे ना।
you can make again a small and very few nodes only, around 70,000, 80,000 only. Otherwise, it will create the problem. CFX, so don't this is CFX, no. What is the problem?
इसकी मशीन रिसेट नहीं हो रही है
फिर से बना लो ना, एक डायग्राम फिर से बना लो, 5 मिनट लगेंगे. न्यू बना लो. यस. Actually, there is some problem. We may create the high number of nodes, so it's not opening further. So we will making it again. It will take only 5 minutes. So this will help you. We are repeating the same step.
कल तो मैगी ज्यादा दी थी आपने.
Yeah. So line by line we create the sketch. So line by line sketch has been created. So now we will do the dimension. So the height is 0.35 mm and width is the 0.2 mm. And the length is 5 mm only. This again has been it has been created. Now we will make the use the fill option to create the domain, fluid domain. So we have created the two domain. One is the fluid domain, other is the solid domain. Now we will do the meshing. Make only few nodes, around 60,000, 80,000 only. That will not create the problem. So we are doing the inflations. We will generate the fine meshing at the joints. You can take only the one domain. Okay. Now the matching is started. So now the total nodes is around 52,000 only. So that would be help us to do the fast simulation. Now you can do the naming. This is the inlet. This is the outlet. And this is the base. Now we will go to the next step. You can update it. Yes. Now it is going well. Now we will open the tab. We will click on that setup. So in the setup, we will do the material selection. We can change the properties, thermophysical properties of the material or fluid domain, and we will put the boundary conditions. So in this we can use whether it's the transient or is the steady. So we are choosing the steady, and we can use the gravitational force also. But this is a very small system, so we are ignoring the gravity. Now we have the different models is there. So we have to activate the energy equations. This is the single phase fluid, so we not going into the multi phase. So the energy equation is activated. Now we have the different model is there. Viscous model, viscous SST. Yeah, yes. So since the velocity is very small, so there is a laminar flow. So we can choose the laminar flow. We can use the turbulent flow. There is a number of turbulent flow is there. And now we have the material selection. So we have two domain. One is the fluid domain, one is the material domain. So we have the fluent database material directory. So we can choose the material from here. If we do not found any material which we required, so we can put the values of the different properties. So we are choosing the water as a liquid, so it is available in the material directory. Now the we can rename the name of the fluid. There is a air is written over there. You can change the name of the fluid. Air you can rename the water.
So we just added additional fluid into it.
Okay.
So we will
Okay.
use the
Okay.
liquid.
Okay. Good. Okay. So we have added the water liquid. There is a solid domain is there, so it is taking the default as a aluminum. So we can change the other material. So what we right now we are taking as the aluminum as the solid domain. Now we have the zone condition. We have to define, we have two different fluid, one is the air, one is the water, and one is solid. In this process we are defining the material. The in the fluid domain we have taken as the water as the liquid, and the solid domain there is only one option is there, the only aluminum. If we want to add the other material, so we can first add into the material section, and then we can include into the cell zone condition. We can change in the cell zone condition. Now we have the boundary conditions. Now we have the inlet boundary condition. Inlet boundary condition, we have a different option is there. So there is a different phases we have found in the boundary condition. So we have rename of the one phase where we have to put the fluid inlet. So it is named as the inlet. So we can change the name of this phase also here, and we can define the boundary type of the boundary condition. So we are taking as the velocity inlet here. So we have to define the velocity magnitude here. So you can give 0.02 meter per second, yes. And if you want to give the fluid temperature, so you can give. So we are taking as a 300 Kelvin. So at the outlet, there is a different phases is there. So we are only interested into the inlet condition, outlet condition, and the we have to apply the temperature or heat flux on the base, so it can simulate the heat density at that phase. So at the pressure outlet, we are taking as the gauge pressure 0. That is the atmospheric pressure at the outlet, and we can give the direction of the that flow, and we also give the thermal condition to the outlet also. Now it is done. Now we have to apply the boundary condition on the base. So on the base we have already defined the base in the meshing section. So here we can apply the heat flux, we can apply the temperature, we can apply the convection, we can apply the radiation, we can apply the mixed, and we can there is a combination of the two method by the system coupling. So we are applying the heat flux only. Now the material is indicated here, aluminium. Now we are going to the methods, how it solve the equation. So we have the different solution methods: simple, simplex, piezo, coupled. So these methods are different technique to solve the equations, and these can be used for the different physical phenomena. So these have uh, their own advantage and disadvantage. Now we are using the simple method, and there is a special discretization of the equation is there. So gradient d square method, pressure second order, momentum second order. So we can change the type of the method for each equations also. And this is the solution control. So we can control the solution, how it take time, how much it take time, and how when will it will converge. So we have defined the different values.
Do you need to change the discretization value?
During the we also can change the these value during the discretization. Next step is
Default domain.
default. So now we have we can initialize the simulations. So basically there is a two method is there. One is the hybrid method, one is the standard method. So generally we use the hybrid method and we can initialize it to start the process. Now we can run the simulations. Now we can run the simulations. So we can put the number of the iterations here. We can put the number of interval. Suppose we have to see the result after 10 interval. So we can put the 10 at the reporting interval, and we have to now the default is the 1. So at the every step we will see the conversion rates here. 100 iteration. Now the simulation is started. Now it is started. So at the end of the 100 iteration, the solution will stop. So we are getting the residual value of the each component: continuity equation, continuity, x velocity, y velocity, and the energy. So we have fixed the criteria. When we our criteria is made with these values, so automatically the simulation will stop. So it is converge at the 54 iteration. So we can see the result now. You can go to the post that post processing. Now that we have complete the models creating, then the meshing, then the setup, and we have completed the simulation solutions. Now we can see the result right now.
Solution
Yes, you can update it. Hmm.
100 से नहीं start करनी थी.
Now you can open the project. Now we can see the result. Yes. So this is the CFD post where we can see the contours. So we have to create the plane in the fluid. So by creating the plane, we are creating the plane. So that is parallel to the YZ plane. Parallel to the YZ plane. Now YZ, you can take the YZ plane method, na? Yes, in mm. Yes, you can take 0.1. Yes, that will create the plane at the mid of the fluid domain. You can see there is a fluid domain plane at the fluid domain. So here we can see the temperature. Now we click on the contours. So temperature we can rename it. Fluid on the plane 1, and we can see the temperature local. This you can take at the range global. Yes. Now this is the temperature of the fluid domain. At the initial, the temperature is low. That is, the temperature is 300, and it reaches up to 1.1227 into 10 to the power 3. But we have taken the very huge amount of the heat density is there. So that's why the temperature is reaches to high, and we taken the single fluid is there. Otherwise, we have to take the multi-phase fluid, dual water and the steams. You can show the pressure on the same plane. You can just change the variable. Instead of the temperature, you can take the pressure. Yes. This is the pressure control at the inlet. From the left side there is the inlet, and the right side is the outlet. So you can see the pressure is continuously decreasing, and it reaches at the outlet is about the zero gauge. That is the atmospheric pressure. You can see the temperature at the base where we have applied the heat density. You can see the temperature only. Local. Now this is the base temperature. So when the fluid is flowing from inlet to outlet, the temperature is increasing, because at the inlet there is a high temperature difference is there between the fluid and the wall of the micro channel. When this extracting the heat, so it temperature rises. So the at the high temperature it not able to extract the heat. That's why the temperature of the outlet is too high. This that is the basic physics uh, behind this. Now this is the contour basically. If you would like to know the values at the particular area, so you can find in the previous solutions. In the post CFD that we are showing here, we can see the only the contour is there. We can also make the graph in this post CFD. Now this is the one CFD simulation of the in the steady state. Now we have the other simulation. In the other simulation, we can take the problem of the phase change material that we have storing the energy into the material that is melting with the time. When we apply the heat energy, so in this tutorial, we will take the two dimensions CFD simulation. So that will be easy to use and it will take less time. So this is done by the previous simulation done by the my project fellow in Zimam. Now my trainee student Saurabh is doing the CFD simulation of the transient phenomena of the phase change material. So you can open that. You have. So basically, heat exchanger is there where we have the phase change material. So in the there is a two shell is there in between the two shell. There is a phase change material is there in the inner cylinder. Inner cylinder there is a hot fluid is flowing there. So it's hot fluid is transferring the heat to the phase change material that is placed between the two shells. So this is the basic geometry. So we will create into the two dimension and then we will do the simulation and we will analyze the CFD simulation results. So we can generate the two-dimensional geometry. It is in micrometer. So there is a one circle is there, and we have the diameter. We have given the dimension that is 40 mm dia, and we can draw the another circle that is the inner cylinder. The dimension is. So basically, these kind of the phase change material, heat exchange having the phase change material generally used in the solar thermal system, not in the solar thermal system. Different industries where we can store the energy into the phase change materials. So one dia is the outer cylinder is having 40 mm dia, or inner cylinder is having 20 mm dia. So we are making into the 2D. So I have created the domain where we have to put the phase change material. So this is a shell type. Now this is the geometry, basic geometry 2D and dimension. Now we will do the meshings. Now the matching has been done. You can see that discretization of the domain. So very fine matching has been done. Here you can see the total nodes here. Uh, it is 11,328 because this is the two-dimensional geometry, so the nodes is too less. Now you can, now we will naming of the different section here. So inner space is the inner edge is the inner line. We can change, rename the name of the edge. This is the outer line. Basically, this is the phase change material. Now we will go to the next step, setup, where we can put the different values of the phase change material, and we can apply the boundary conditions here. Basically, this is the transient phenomena is there. So the phase from solid to liquid is going will be changed. So we have taken at the transient. Now we have applied the gravity also in minus 9.81 in the y directions. Now we can on the energy equations, and we can apply the models. Now we have to apply the solidification and melting. So here we can change the uh, parameter as desired. So here in this we can change the fluid. What is the fluid or what is the solid is there? What is the material? Basically, phase change material is there. So if we do not get the particular material into the directory, so we can create it. So we are creating the phase change material using the physical their thermophysical properties. So this is the density, specific heat, thermal conductivity. The thermal expansion coefficient. So we have to put if we do not find into the CFD directory. Now the phase change material has been created. Now we will apply, select this phase change material into the our domain. So we have named the surface body. So we can select the material as a PCM which is generated. So this is the boundary condition. We have basically three parts there. One is the inner line, one is the outer line, one is the surface, uh, inner surface, that is the phase change material. So we will apply the boundary condition at the inner line. That is where the fluid is flowing. So we can put here the temperature. So uh, we can apply the heat flux. We are placing the putting the temperature 329 Kelvin. So as per our requirement, you can put the boundary conditions. So in the method, we can apply whatever the method is applicable. So coupled is applied for this particular problem. So in the surface report definitions, you can see the result simultaneously when it is converging. So temperature has been taken in the surface report definitions. Now the further we have taken as the other apart from the temperature, it is the solidus, solidifications and melting. हेलो लेक्चर चल रहा है. So these are the residual monitoring. So we can change these value if we need the more precise, accurate accuracy in the result. So we have to change these values. Now that we have initiated the initiated the solutions, so the solution it is different from the previous one. Here, because this is the transient method is there. So in the in the calculation, we have to define the time step. So at every 100 degree, 100 time step, zero time step has been taken 0.1, 0.5. For each time step, we have taken the maximum iteration of 25. So it is slightly different from the previous one. 100 time step has been taken and the each at the and the time step of each step is 0.5. The total time required to do the simulation is the 50 seconds. Now the simulation is started. So you can directly see the result here. You can the total temperature right now, solidification and melting. Click on this tab, na solidification and melting. This one.
There is some errors during the setup.
Okay,
So let me stop it.
you can stop here, no problem. You can reinitiate the solution. Now the simulation is going on. Is there any problem?
Yes, sir, it is not converging as it should be, and it is not going
You
to
can
the
open the post CFD na.
but there is only the single right?
You can open your previous file, which I had already simulated. You have. You can open that. But there is some problem in the current simulation. So we are opening the simulation we have already done. You can do. You can open that file, na. You can open that file. Yes. You can do. You can take only 5 minutes. in the previous model there was some problem, so it is not converging, so we are making the another model. You can update it. You can refresh. Saurabh, you can open the previous one. That is not. No, right now we have done now.
He is not able to find that
Error.
point. And in that system, he is not able to find the error. What is the
It's okay. There is a problem in the setup. There is a, you can reopen it. You can close and you reopen. You can reopen. You open this trial to the previous one now. Match is already done. You can go to the setup directly. Hmm. Actually, there was some error, so we are not able to find it. What will be the error? So we are doing the again. On the energy equations. You can put the temperature here. You can check whether it has been put the temperature. It is fine. Now you have to put the thermophysical property. You skip that step. Don't put so much parameter. Just 2 and 3 is enough. You can put the material property. No? It is done. Material property is important. No? And you active with the melting and solidification. Done? Okay. So the solution method is again initialize. Meanwhile, you can show the result you have already uh, in the Word file, na? Yes. So these are the result we will get it. So basically the you can see the first case at the 100 after the 100 second. So there is a fraction of the liquid is very small at the inner surface of the inner cylinder, and when the temperature is time is increasing, so the fraction of the liquid of the phase change material is increasing. The red one is showing the liquid phase, and the blue one is the solid phase. So this is the temperature we are we will got. So when the temperature is increasing, the time is increasing, so we are getting the higher temperature on the other side. Here, this one. So now the simulation is going on. So you can show this solidification. Yes. And now it is going well. The liquid fraction is increasing with the time. As the time increases, the liquid fraction is increases. So we will, after completing the simulation, we will show in the contour form. It is about to complete. It is 50 seconds is there only. You have taken one time step. So you can stop here. You can stop here and show the result, the contour. You can open the CFD post. Don't close, just minimize it. Open the CFD post, yes. So you can continue here only. Or you can decrease the time step, number of time step. Basically, you have taken the 200. You can limit up to the 70 only time step. Uh, it will take time. That is started the solving again. That is completed, na. Close all for me. Yes. You can wait. You have taken long number of time step is too high. It is going on. You can wait. It no, it will go up to 2000 iterations. 4000 iteration it will go. You have taken lot of. You can stop here, na? You can stop from that window. You open the other window.
Actually, the workbench is installed for this.
Yeah, you can.
Is that- it
Oh, it
not-
will.
it is not
It is
working.
hanged basically. Four thousand. Now you can see the here the result. The time is it will go up to the 200 seconds. So right now we have reached up to the 120. So after going to the 200 second, it will stop. So the liquid fraction is increasing.
तो ये तो वो कर नहीं पाएगा लैपटॉप संभाल नहीं
You can open that result. हाँ, वो show कर दो. Yes, so we are get the this result. Basically, these are the we have done previously, but we will get the similar result in these heat exchanger. We have taken the fins uh, 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 on the top side and the bottom side of the inner tube. So you can see we have got the result up to the second. So after the 50 second, the about 70% of the solid PCM is has been melted. So this is the other contour that is the showing the temperature. So temperature is goes up to the 329, which has been put into the setup. You can see the next. So this simulation has been done when the fins are placed side by side. So it is the effect of the this fin. So we also place the four pin on the top, bottom, and the left and right of the inner cell. So these are the some result we are previously simulated. Next. So these are the different kind of the fins has been taken, and we have simulated the phase change material. So we also calculate the how much amount of the energy can be stored in the phase change material by simulating these simulations. You can check whether it is working or not. It is going. Okay, meanwhile, it is going to stop after 4000. You already 6 o'clock is time is there, so you can if you have any question or regarding the simulation, so I will happy to answer you. Dr. Ravi,
Yes, sir.
actually these
Yeah,
simulations
participants,
taking a lot
if you
of.
have any query regarding software simulation, yeah, how to design and how to select the geometries and other parameters, please ask the experts.
Actually, we have done the simulation on the simple laptop, so we have to go for the workstation. So that is the problem occurred. So it's not responding, the laptop is. Although we have successfully conducted the simulation of the previous one, but it is this simulation is creating the problem because it is the high-end computational simulation due to the transient phenomena is there. If you have a question, audience, if you have a question, so I will be happy to answer you.
Sir, I just asked the question. How this CFD analysis help architects in optimizing the natural ventilation and thermal comfort in building design? Regarding the CFD helping thermal building design, this wall design and other parameters?
Yeah, basically in the CFD simulation can be help in the two ways. First, in the designing of the envelope of the building. So basically, in the designing of the envelope of the building, we need to consider the heat transfer. So we can simulate the building envelope with the actual one. So we have to simulate the solar gain to the building through solar gain into the building through the wall or roofing and glazing. And the other point is the ventilation simulation of the ventilation. So ventilation of the simulation, that is the fluid flow phenomena, that can be simulation that can be can we can do the simulation in the CFD ANSYS Fluent. So basically, the movement of the air from one end to the other end of the building by the help of the some force ventilation system can be done. So there is a lot of module is available in the Fluent, like fans, like blowers. So these module will help us to simulate the CFD simulation of the natural ventilation, force ventilation as well as the natural ventilation also.
Sir. And sir, also can this CFD used to evaluate the performance of passive heating design, the passive design strategy of solar passive heating in buildings?
Yes, of course. Basically, the every parameter that can be calculated. Because this is the numerical technique, so there is a lot of parameter, like we have the diffusivity, we have the solar gain, we have the conductivity, we have the heat capacity, we have the different parameter is involved in the in this numerical techniques. So the heat gain into the building or heat removed from the building can be calculated easily. There is we have published few papers on that. So we have we have analyzing the solar thermal system also, and simulation of the building also.
That's all from my side. Participants, if you have any queries, please ask the experts. Otherwise, we are going to end the session now.
I have one question.
Yes,
Please
yes,
ask the question.
Hello.
yes, yes, sir. You are audible.
I have one question. I would like to ask, sir, how
Yes.
like it means sandwich plate with isotropic skins with viscous elastic core can be modeled in ANSYS, because considering viscoelastic core, that is a linear viscoelastic core, how that can be modeled in ANSYS, sir? Can you tell me?
Basically, porous model can be modeled. Porous material, the property is not thermophysical property is not constant. So there is a variable in the thermophysical property. So we have the user defined function available in the Fluent. So we can define the properties, thermophysical properties, which are variable due to the temperature, due to the spatial variation into the material. So we can make the program, we can make the program into the MATLAB, and then we can export these program into the Fluent. So we can do we can do the simulation where we have the variable thermal physical properties of the material is there. I
Thank you.
even we have, if we would like to apply the variable boundary condition of the thermal in the thermal system, so we can make the coding for that also.
Thank you. Thank you, sir. Thank you.
So thank you all for your enthusiastic participation for the today's hand-on session on CFD analysis of thermal system using ANSYS Fluent, led by the Dr. Tabish Alam, Senior Scientist at CBRI Roorkee. And we extend our heartfelt thanks to Dr. Alam for providing a highly informative and practical sessions. Participants gained a hand-on experience in designing thermal system models, selecting key simulation parameters, generating geometries, and performing CFD analysis using ANSYS Fluent. And the session offered a deep insight into how these tools can be effectively applied in the energy building designs and analysis. So we hope today's session has equipped you with the valuable skills and encouraged you to explore the simulation approaches in your research and professional practice. So thank you, sir, and thank you all the participants. So now with this, we close the meeting, and we will meet tomorrow in the morning. Okay, thank you,
Thank
everyone.
you. Thank you.
Thank you, sir.
क्या है हाँ तो तुम वैसे नहीं कर पाया